Yes or no? Familiar or not familiar? Not familiar. Okay. So probably I will very quickly go through that. So today I will introduce the notion of partial order first. Okay. So this is a generalization of the notion of less than or equal to on R. The notion of less than or equal to, when generalized, gives you the idea of partial order. So let us define what it is. So definition, let X be any non-empty set. I assume you all know what is meant by a relation, so I will skip that. Then a relation which will denote by this symbol, a slight generalization of the less than or equal to symbol, is said to be a partial order on X if certain things happen. Okay. The same thing that happened to less than or equal to happen. That is, one, it is reflexive, that is, X is related to X for every X in X. Okay. Two, it is antisymmetric. We will see some explanations for these words a little later. That is, X is related to Y and Y related to X can happen only when X equal to Y. Of course, in this all these X's and Y's are assumed to be from the set X. Okay. 3, it is transitive. That is, X is related to Y and Y is related to Z implies X is related to Z. So I will take all X, Y, Z above or in X. Okay. So this is just like if for every real number X is less than or equal to X, if X is less than or equal to Y and Y is less than or equal to X is equal to Y. If X is less than or equal to Y, Y is less than or equal to Z, X is less than or equal to Z. So these are the typical properties of the less than or equal to, and the same properties, if they are copied, it is called a partial order. Okay. Then the set X together with a partial order is called a partially ordered set. And is denoted by that pair. So it is a package, the set and the relation. You may have the same set but some other relation, then it becomes a different partially ordered set. As a set they are same, but as the shortly we say, instead of partially ordered set, we short say poset. Okay. The first thing is examples. Okay, so let's. I will give. There are many examples which you will see in any course on discrete math. So I am going to give one or two examples. That's why. So and one or two of the examples will be what we will be looking at a little later also. The first example is a typical example which will be useful to us. Okay. So let K be any collection of sets K is a set and each member of the set is some set. So, it is a collection of sets, and for AB, for any AB in K, so what are A and B? A and B are sets, okay, and K is the collection which contains all these sets. For A and B in K, we say A is related to B. So, I am defining a relation if A is a subset of B. A is contained or equal to B. Okay. So, the subset are equal to, and it turns out this is a part very easy, because if A is contained in B, A is contained in A for every set, A is contained in B and B is contained in A, then A equal to B. If A is contained in B, B is contained in C, A is contained in C. So, clearly this is a partial order on K. So, on any collection of sets, the subset are equal to E is a partial order on any collection of sets, okay, and K with this partial order is a let me give you another example, which is a specialization of this, okay. So, which again I will come back to. So, let V be any vector space. Assume we all know what is meant by a vector space over any field F. If you do not like, take it as R or C. If you do not like general, you are not familiar, take over the scalars to be real numbers or complex numbers. Let V be any vector space for a field F, and take a special case of this. Let K be the collection of all linearly independent sets. We will explain little bit more about linear independence later, okay. So, the set of all linearly independent sets in V, and since subset are equal to partial order on any collection, in particular on collection it will be a partial order. So, K is the partial. Of course, less than or equal to is a partial order, because that is the one that motivates. Less than or equal to is a partial order on the real numbers, on the rational numbers, on the integers, and so on and so forth. I will give you two more examples, so that whenever you have some terminology in partially ordered set, you see what it means with respect to these examples. Let us deviate a little bit from the sets. I will come back to the sets again. So, let us take X to be the set of all integers, positive integers. Okay. You already know that less than or equal to is a partial order, but I am going to look at another partial order on the same set. So, as set it is same, as partial ordered set I am going to look at a different partially ordered set. So, for m and n, two positive integers, we say m is related to n if m divides n. What it means, that is m is a factor of n, okay, or n is an integral multiple of m. So, if m divides n. Now, we can see that that is partial order, because every number divides itself, is reflexivity. If m divides n, n divides m, obviously m must be equal to n, and if m divides n and n divides p, obviously m divides p. So, it is clearly a partial order. Okay. So, this is a partial order. On n, and therefore, partial order is a poset. This is different from the poset n less than or equal. The carrier set is the same n, but the order is different. So, as partial ordered sets they are different, as sets they are the same. So, on the same set n, on the same set you can have several partial orders, and as partially ordered sets they will become different. Now, I make one remark before I give some more examples. Now, from these two examples itself we can generalize. The first remark is, suppose you have a partially ordered set. I have a partially ordered set. Now, what I am going to do is I am going to take a subset of x. Take any subset of x, and the same relation is also a partial order on the subset. So, all these properties hold all over x. So, in particular in the smaller universe. Then this is also a partial order. Of course, I am taking x1 to be non-empty. Partial order on x1 and x1 with this partial order is also a poset. So, there is a big poset, inside that a small poset is sitting, and the small poset using the same order that it had originally living in the bigger world. We call this as a subposet, is called a subposet of the original poset. Now, first of all, why is it called a partial order? It's because it's not necessary that two elements are comparable always. Given x and y, we may have neither x is less than or related to y, nor y is related to x. So, it's not that it's ordering everybody, it's only ordering within a few groups only. So, it's partially ordering things. Okay, so given x, y in a partially ordered set, it may happen that neither x is related to y holds, nor y is related to x. Okay. And what antisymmetry says is that if we add two distinct elements, both cannot happen. If x and y are different, then x is related to y and y is related to x, both cannot happen. Okay. So, like, you can think of an example like that. Let us say we have members of a family, or the men in Bangalore, and I say man X is related to man Y if X is younger brother of Y. Okay. It may happen I may pick two fellows, neither X is younger brother of Y nor Y is younger brother of X, and if by chance X is younger brother of Y, then Y certainly cannot be the younger brother of X. So, if one happens, the other one cannot happen, but it may be that both do not happen. So, the antisymmetry really says both way relationship is not possible. Both way is not possible and both need not be true, but one way may happen. That's all. Okay. So, if by chance, if x and y, are such that either x related to y or y related to x happens, then we say x and y are comparable. Or comparable. So, one of them will be related to the other. So, what happens is, given two elements, they may be comparable, they may not be comparable. Given two elements in a poset, they may be comparable, they may not be comparable. Let me give you one more example, which a little bit more sophisticated version of that example we will use later, okay, when we actually do functional analysis. Okay, what is the example number now? 2, 3, 4. Let me describe this example a little bit more carefully. Consider two sets, be any two non-empty sets. So, I have A here, I have B there. Consider two sets A and B. Then now I am going to look at all functions, but the function that I am going to consider may not be defined on all of A, but only on a part of A, but it will always end up in B. So, we look at functions whose domain is a part of or all of A. We do not know, but it may be a part of A also. So, it is a subset of A. So, we look at all functions whose domain is this and codomain is B. The values are always in So, there will be functions like this, there will be a patch and they are all functions from there to there. That patch is called the domain or definition of the function. So, you know that every function is clearly has two parts, one called the domain and other called the codomain, and two functions are said to be equal only when the domains, codomains are equal and the corresponding values are equal. Okay, so now I am going to take all such possible functions. Okay, so let f subscript a b be the collection of all such functions. It is all the functions whose domain is part of A and codomain is B, and that domain part may be very different functions. So, all possible functions whose domain is part of A and codomain is B. Is the definition clear? Okay. Now, I am going to define a partial order on this. Okay, so, we now define a partial order on this set of all functions. We are going to do. So, we are going to say n is a function, such a function related to another such function. Okay. So, I have a function whose domain is say df and the function is f. So, I have a function f whose domain is df and domain is b, and I have another function whose domain is g and codomain is. So, both these functions are going to end up at b, but a f is defined in some part of a and g is defined in some other part of b. So, we say f is related to g if something happens. See, intuitively the notation says f is smaller than g. What is meant by smaller? It has less information. So, what it means is this domain is smaller than this domain. 1, df is contained in dg, and whatever information f has, g has same information. That is in the common part. So, now how does it happen? G is going like this. Now, df is part of this, f is going like this. Now, in this part both f and g are make sense and they must coincide. Okay, so, and the parts where they are both defined, they must be equal. Fx equal to gx for every x in g. This is what he said, that g is an extension of the function f. So, we simply say g is an extension of f. Now, extended the function, then extended losing the old values. Okay. So, we say f is related to g if g is an extension of the function f. Now, verify that this is a partial order. See, first of all, f is less than or equal to f because df is contained in df, and this is obvious. And then if both are satisfied, then df and dg are the same and the values are the same, and therefore the functions are the same and transitivity is automatic. So, clearly this is a partial order on FAB with this partial order the poset. Okay, now I am going to specialize on this. Remember, I said that if you take a poset and if you take any subset of the poset, that becomes a sub poset with the same partial order. So, now in this collection of functions, I am going to take a special collection of functions, and that also will be a partial order with this extension relation. Okay. The moment I have a relation on a big set, that is also a relation on a small set, that is partial order, this is also partial order. So, let us call that as example now 5. Fix a function f in FAB with domain df. So, what I am going to do is I am going to consider one particular function whose domain is df. I am fixing that function f. Take one particular fixed function whose domain is fixed. Okay. Now, I am going to look at a set EF look at all possible extensions of F. That is all those fellows such that F is related to G. So, this is the set of all G in FAB such that F is related to G. Okay. The set of all possible G, F is related to G means a G is an extension of F. So, in other words, I am looking at all functions which are defined on sets bigger than or equal to df, and in the part df same as the old value f. Okay. So, we are looking at all possible, the set of all possible extensions of the fixed function f. Okay. So, that is why the symbol E, extension of f. Then EF is also a part, the EF less than or equal is also a partially ordered set. Also the same extension relation is a partially ordered set. Say that again. Yeah, obviously, that is what I said. Whenever you take a subset of a poset with the same relation, it becomes a subposet. It is also a poset, a subposet of, yes, that is correct. Whenever you have a poset and a subset, the subset becomes a poset with the same relation, and then it is called a subposet. Okay. One important chapter in functional analysis is about extension of linear functionals with certain properties preserved. Okay, and that is why I introduced the notion of extensions of functions. Okay. The next notion that I will introduce, these are all examples. Now we know what is a partially ordered set. We have defined what is a partial order, and we have certain examples. So, we have something to work with whenever we want. Okay. We made one observation, namely that if you have a poset and if you give me two elements in that, it is not necessary they are comparable. Okay. So, recall that in a poset X, a pair of elements X y need not be comparable. But consider this poset. The example that we had, the natural numbers, the divisibility. Okay. M is related to n if m divides n, that poset. In that, you consider the following subset. Consider the subset say 2, 4, 20, 140. Just like that, some subset like that. Now, if you look at this subset, here any pair of elements is comparable. You take any pair, 2 and 4, 2 is related to 4 because 2 divides 4. 2 and 20, 2 divides 20. 2 and 140, 2 divides 140. 4 and 20, yes. 4 and 140, yes. 20 and 140, yes. So, any pair of elements is comparable. In this subset, every pair of elements, what is the correct grammar? Every pair is comparable, or every pair of elements are comparable? Is comparable. Because pair is the noun there. Okay. So, even though the original in the original poset there are uncomparable pairs. The original poset is this, for example, 5 and 18 are not comparable. Neither 5 divides 18 nor 18 divides 5. So, even though the original poset, not every pair is comparable, there are subsets in which pair is comparable. Such subsets are called chains. Okay. So, this is the definition. This gives us the definition. That is, this subset now is a poset, subposet with the same. So, this subposet has the property that every pair is comparable. So, the big poset, not every pair is comparable, but if you restrict it yourself to a smaller universe, things are nice there, every pair is comparable. Such smaller universes are called chains. Okay. So, definition: in a partially ordered set, a subset, a non-empty subset, C is called a chain if every pair of elements in C is comparable. C is comparable. So, can you tell some chains in that poset? For example, if I take all the powers of 2, 2 squared, 2 to the power of 4, 2 to the power of 7, 2 to the power of 8, then every pair is comparable. That is a chain. Okay. So, now we many chains. So, even though the original poset is somewhat disorganized in its order, there are fellows who are not comparable. Here they are neatly organized. There are certain smaller universes which are neatly organized where every pair is comparable. Such subsets are called chains. We will look at some chains in this example also. Okay, as we finally, as I do as an example, we look at some for the Zorn's lemma. Right. So, I am going to introduce one or two more notions before I will state the Zorn's lemma. These notions are almost like what we do in real numbers, but there are certain traps. You should not fall into those traps. Okay. So, the first notion is the notion of upper and lower bounds. So, suppose I have the set of all real numbers, in that I have a small collection, and then what do I mean by saying some number is an upper bound for this collection? Means that nobody here can exceed him, or everybody here is smaller than him. The same notion, now instead of smaller we will use this symbol, that is all. So, let X be a partially ordered set and S a subset of X. Okay. So, I am going to take a subset of X, then I am going to introduce a number of terminologies. 1, an element U belonging to X, that U may or may not be in S. I started with a subset S, but now I am looking at an element which may or may not be in S, is called an upper bound for S if obviously every element of S is dominated by U, okay, for every S in S. Think of this as your usual less than or equal to for definition purposes. And an element L belonging to X is called a lower bound for S if what? The other way around, L is smaller than S for every S in S. So, we have this notion of upper bound and lower bound. Then I will introduce the notion of a very tricky notion of a maximal element. Okay. An element, watch the definition carefully, an element M belonging to X. Okay, I will introduce, let me restrict for the time being only for upper and lower bounds, because that maximal is with respect to the full poset. I am looking at only the sub poset. I am not going to introduce the notion of least upper bound, greatest lower bound. Ideas are the same. At the moment, I need only the notion of upper bound. Okay. Think of this as a subset of FAB and say what will be an upper bound for this. Just think about it. Okay, I will later. So we have the notion of upper bound and lower bound. I have not said the upper bound or the lower bound. There may be many upper bounds. There may be many lower bounds. There may not be any upper bound. There may not be any lower bound also. So we may have very key situations where, for example, take this, take all the powers of 2, 2 to the power of 0, 2 squared, 2 squared, 2 cube, 2 to the power of 4, etc. So all the powers of 2 as your subset. Does it have an upper bound? No, obviously it does, but it has a lower bound, namely the 2 to the power of 0. Okay. So it may have an upper bound, it may not have an upper bound, it may have a lower bound, it may not have a lower bound. I am not saying if there exists such an element, it is called an upper bound. If there exists an element, it is called a lower bound. Okay. The next notion I am going to introduce is a maximal element in a poset. So this is the last notion I introduced before I can state the Zorn's lemma, maximal element in a poset. So an element M belong to the poset is called a maximal. There may be many maximal elements. A maximal element if what could be the normal, what could be an intuitive definition? Huh? None of the elements should exceed that. So let me put it that way. If somebody exceeds him, if there so okay, if A belongs to X and he exceeds A, these two together must, the only possibility is is equal to. If anybody can be related to him, only he can be related. Nobody else can exceed him. Think of this as less than or equal to. Pardon me? Wait a minute. Yeah. A belonging to S, M less than M equal to, that is called a maximal. Okay. It does not say that A is smaller than M for every A. No, it does not say it is a maximum. It does not say it is maximum, it only says it is a maximal element. Nobody can exceed him, it does not mean he exceeds everybody. That is why it is partial order. Okay. So, its logic, language is all different now. Nobody exceeds him does not mean that he exceeds everybody. Tricky, because it is partial order. Okay. There will be somebody who is not related to him, so that is you are trying to compare an apple and an orange. Okay. So, one of the fundamental problems is about when does a partially ordered set have a maximal element, when can it guarantee, and that is what Zorn's lemma says. Zorn's lemma gives you a guarantee of the existence of a maximal element for a partially ordered set under certain conditions. So, Zorn's lemma connects all these things. If in a partially ordered set, every chain has an upper bound. So, I am linking all the terminologies we have introduced. We introduced the notion of a partially ordered set, we introduced the notion of a chain, we have now introduced the notion of an upper bound. Now, then the poset has a maximal element. The poset has a maximum. If in a partially ordered set, every chain has an upper bound, then the partially ordered set must necessarily have a maximal element. So, let us look at one or two examples. Understand this. First, I must have a poset. In that poset, I must verify that every chain has an upper bound. Then I can conclude the existence of a maximal element. It looks like a horrible task. I have to verify that every chain has an upper bound and all these things. But then you are trying to reach the peak, the maximal element, you got to work hard. Okay. So, let us look at some very simple example to understand these terminologies. Okay. Any questions? Is it possible to count the number of chains? If X is a finite set. Okay. X is a, you see, finite thing, counting is not at all a problem. Okay. It's an infinite thing that the countings are all problematic. After all, what is there? You can list all subsets and simply pick out all the chains. It's not a big, see, after all, in a finite thing, give me enough finite time, I list all of them in a way. Okay. And then give me finite time, I will pick out all the chains. So, basically what it says, things handleable, not a big thing. Okay. Particularly these days, a brute force computer listing can pull out everything. And of course, a clever person will do it in a much cleverer way. Okay, where was I? Anyway, the job is not to be counting these things. That's a combinatorics course or a discrete math course. So, I am not going to spend counting them. Now, let me just illustrate these terminologies and other things for some examples. So, let us look at some example. Let us look at the poset EF we had with the same notation. What is it? It is the set of all extensions of the function f from a to b. F was a function which domain of df, and was mapping df to b, and I am now looking at all possible extensions of f. So f is the set of all g in FAB such that f is extended by g, or g is an extension of f. Now intuitively, what is meant by a maximal element here? Let's figure it out. Okay, so there is a, here is b, and here is df, and f is mapping from this to this. Now all these g's are functions defined on df or bigger than df. So what is maximal then? So a function which is defined on all of a such that its values coincide with the values of f on the set df. That is a maximal element. So maximal element, so any function h mapping a to b such that hx equal to fx for every x in a is a maximal element. Okay. Now, by the way, how do I know this h is in EF? Because that is also an extension of f, and therefore it is in EF. So an element in the poset. Okay, this h is in this poset. So I am looking at this poset. In this poset, there is an element, and that is such that nobody can be beyond him. Nobody else can be beyond him. It's a maximum. So we will be looking at in future will be about certain types of functions which we need to extend. Okay. Okay. Now let me give you one typical useful example of the Zorn's lemma. Very, very useful example. So an example of Zorn's lemma. And we will be using this type of argument many times. Okay. So I have a vector space V. So let V be a vector space over F, over a field F. If you don't like, if you are not familiar with fields, take with scalars to be complex or real numbers always. Now we have the notion of linearly independent sets in a vector space. When do I say a set is linearly independent? Yeah? Good. So therefore, somehow or the other our mind goes back to linear combination. The moment I say linear combination, I can't be writing an infinite series. Because in the vector space, I don't know what is meant by convergence of the infinite series. So I am stuck with finite. So first of all, I will talk about the notion of when do I say a finite subset is linearly independent. Okay, so a finite set of vectors V1, V2, Vk is said to be linearly independent if the only linear combination that gives the 0 vector, I will call theta v as the 0 vector, if and only if alpha 1, alpha k are all 0, where all these alphas are from the field F. If you are taking real vector space, alphas must be real numbers. If you are working with complex space, alphas must be complex. If you are working with any arbitrary field, those must be from that field. So we all know this. But then when do I say an infinite set of vectors is linearly independent? There is a little problem. I can't say, first of all, I don't even know whether that infinite set is countably infinite, so that I can write it as a series. It may even be an uncountably infinite set of vectors. How do I say they are linearly independent? So what I do is I fall back on finite set. So this is the definition. An infinite set of vectors in V is said to be linearly independent if every finite subset of S is linearly independent. The moment I come to finite subset, I know how to check linear independence. If every finite subset of S is linearly independent. Okay. Now that definition subsumes this also in a sense, because in a finite set it is linearly independent if every subset is also linearly independent. That is the definition of an infinite linearly independent set. Maybe I should give an example. Okay. So, just to illustrate what sort of difficulties we may get into, let me take, so here is an example. Let us take all functions from R to R, or even 0, 1 to R. Okay, R to R, whichever you want, it does not matter, all are of the same cardinality. Let us take all real valued functions defined for all real numbers, all real valued functions from R to R. This is a vector space, because the sum of two such functions is a function, scalar multiple of such a function is a function, and so on and so forth, is a vector space over R. The field now is R. So the collection of all real valued functions over R is a vector space. Now I am going to look at a huge collection of functions. For a, here is the number, here is the real line. Take any real number t and then make the function 1 there and 0 elsewhere. So for every t in R, we have a function ft belonging to FRR defined as f of x is equal to 0 if x not equal to t, 1 if x equal to t. Get that thing? So I have for every time a function which lights up only at that time and switches off the light at all other times. Okay. So different times produce different functions. It's like the delta. Okay. You are all familiar with it. Now you see how many such functions are there? As many as there are real numbers. Corresponding to every real number I have one switch which switches off. So the collection of t as t varies over R is an uncountable collection of vectors. They are all vectors in the vector space FRR. Okay, they are all vectors. Any element of vector space called a vector. So they are all vectors in that vector space. Now, is this linearly independent? Is this collection, is K a linearly independent set? So what should we do? We check with every finite subset and see whether it is linearly independent. So, let us check with every finite subset. So, what is meant by finite subset? We are going to pick finite number of time points and look at the functions corresponding to those. So let ft1, ft2, ftk be a finite subset of k. So I am looking at those functions. ft1 switches on at time t1, ft2 switches on at time t2, ftk switching on at time tk. There are k time points corresponding to each one of them. I get a function. I want to make sure whether this is linearly independent. So what does this mean? This function is the zero function. That means the right hand side is a function which takes the value 0 for all x, and the left hand side is also a function depending on what time you are choosing. So what it says is, that is alpha 1 ft1 x plus alpha 2 ft2 x plus alpha k ftk x is equal to 0 for all x in R. The left hand side is the 0 function. That means for every point it must take the value 0. Is that okay? Now what do you do? Since this is true for all x, put x equal to t1. What do I get? This is alpha 1, they are all 0. So alpha 1 will become 0. X equal to t2 will give alpha 2 is 0. So evaluating at x is equal to t1, t2, tk, we get alpha 1 equal to alpha k equal to 0, and therefore ft1, ftk linearly independent. So every finite subset is linearly independent, and therefore that huge set is linearly independent. That huge set of functions that we have got, which is as big as the real numbers itself, set that class of functions. Okay, that vector space is very huge. Okay. So therefore k, every subset of k, every finite subset of k is linearly independent, and hence k is linear. That is what is meant by infinite sets being linearly independent. However big you may take, that k may be trillion, and still it is linearly independent. And therefore, that is what is meant by saying an infinite set of vectors is said to be linearly independent if every finite subset is linearly independent. Okay. Okay, I will erase that. Now, take the vector space V, same notation, over a field F, any vector space over. So now let L or K be the collection of all linearly independent sets in V. All possible linearly independent sets you take and put them in V. You put them in a collection, and that's called L or K or whatever. Collection of linearly independent subsets in V. Now, the moment you have a collection of sets, you have a standard partial order, namely subset or equal to. So K, that's the first example we saw. So this is a partially ordered set. Now, what is meant by a maximal element of this poset? First of all, it must be element of this, which means it must be linearly. What does maximal mean? Nobody can be him. That is, this fellow cannot be embedded in bigger linearly independent set. So, in a sense, this is some kind of an optimal size for an linearly independent set. Okay. So, a maximal element in K is a linearly independent set is not a proper subset of any other linearly independent. It cannot be a proper, because if that happens, the moment that fellow must be equal to him. So, therefore, it cannot be a proper subset of any other linearly independent set. We simply call it a maximal linearly independent set. So, such a thing, such a set is called a maximal linearly independent set or a basis. A maximal linearly independent set is a basis, because the moment you put something, that fellow is expressible in terms of these guys, and these fellows alone are linearly independent. Such a maximal linearly independent set in V, a maximal linearly independent set V is called, I would have said a basis if I was teaching a linear algebra course, but if I am going, since I am still to start a functional analysis course, I will call it a Hamel basis. It's called, because we are going to look at other types of basis. Hamel basis. Hamel is the name of a mathematician. Okay, called the Hamel basis for the question is, does the vector space necessarily have a Hamel base? Because we have seen that a partially ordered set need not have a maximal element. So, therefore, this partially ordered set of linearly independent set need not have a maximal element. Nothing assures us yet. So, we do not know whether a vector space will have a Hamel basis. Zorn's lemma gives us, yes, it will have a basis. It will have a maximal element. Using Zorn's lemma, we can show that K is the collection of all linearly independent, has a maximal element, and hence every vector space has a Hamel basis. Okay. So, Zorn's lemma is basically in a sense transfinite induction. I will come back to those later. How do I use Zorn's lemma here? So, in order to apply Zorn's lemma to this poset, what does Zorn's lemma ask? If in a poset, every chain has an upper bound, then there is a maximal element. So, I am given the poset, I want to conclude maximal element. So, the between things, namely that every chain has an upper bound, is what I have to verify. So, we must show that every chain in this collection of linearly independent sets has a upper bound. So, for this Zorn's lemma, it is enough if we show that every chain in the collection of all linearly independent sets has an upper bound. That is all we have to show. Automatically Zorn's lemma says it has a maximal element. A maximal element is, by what we have seen in this poset, is just a maximal linearly independent set, and that is what is called as a Hamel basis. So all we have to do is verify that if we have a chain of linearly independent sets, that chain will have a upper bound. That upper bound must be in this poset, because the upper bound is always in the poset. So therefore the upper bound must also be a what? Linearly independent set. Okay. So therefore verify that. I will just indicate the proof now. So start with a chain. What is meant by a chain? They are all elements here. That means they are all linearly independent sets, and there is a chain. Therefore, given any two of them, either this fellow is contained in that or that fellow is contained in that. Two fellows are comparable. Therefore, A belongs to C means A is a linearly independent set in V. AB belongs to C means either this is what is meant by saying C is a chain in K, that partial order, in that linearly independent set partial order. Okay? That is exactly what is meant by saying C is a chain in this. Now I want to find an upper bound for this. That means everybody here must be subset of this. I want to find a fellow such that everybody here is a subset of that. Can you think of such a set? Simply take the union of all of them. Okay, so let U, the U and the union are very, okay, let U, okay, let me put a small u, be the union of all the sets in C. Take the union of all the sets that form the chain, but the chain is like this, each fellow is contained in the other. Now I claim, we claim U is a linearly independent set. We will show that, and therefore U belongs to K and A belongs to C implies A is contained in C, because this is the union of A is contained in U, because U is the union of all the fellows. So any one of the fellows must be a part of it, which implies U is an upper bound. Everybody in C is smaller than him, and therefore U is an upper bound for C, and therefore we have shown that every chain has an upper bound. What is to be proved finally? That claim that U is a linearly independent set. To do that, what should we do? Every finite subset is linearly independent. So, okay, so that claim proved now. The proof of claim. So, enough to show that every finite subset of U is linearly independent. Right? Because in order to show that something is linearly independent, we have to show that every finite subset is linearly independent. Okay. So take any finite subset. Finite subset V1, V2, Vk of U. right. So, V1, V2, Vk are in U, but U itself is that union. Therefore, V1 must be in some A, V2 may be in some other A, Vk may be some other A. So, therefore, there exists A1, A2, Ak belonging to C such that Vj belongs to. Is that clear? All these fellows are in the union, so everybody must belong to some one member of that union. Now, what can you say about A1, A2, Ak? It is a chain. So, either A1 or A1, compare A1 and A2, one of them will be bigger, throw the smaller one. Compare the bigger one with A3, take the bigger one and go on. Finally, you will get the largest among the K sets, which is precisely the union of A1, A2, Ak. Okay. So, since C is a chain and there are only a finite number of them, this A1, A2, Ak, there exists J such that Ai is contained in Aj for every I. And therefore, V1, V2, Vk are all now in Aj. Okay. Now, what can we say? Aj is a linearly independent set because it is a part of the chain. The chain is a part of the set K and everybody in K is linearly independent. So, Aj is a linearly independent set and therefore, any finite subset inside that must be linearly independent. This is a finite subset of linearly independent set Aj and therefore, is linearly independent and proves the claim. Okay. So, that is how we existence of maximal elements, existence of a basis for a vector space and so on and so forth. Now, look at that one example I gave of the collection of all functions and then I gave you a big linearly independent set. What was that big linearly independent set? Ft, T varying over R. Now, is that a maximal linearly independent set in that vector space? Can you tell me? To recollect. Do you remember that example? I had this vector space of all functions from R to R and I had this set, the set of all Ft, T belonging to R, where Ft of x is 1 if x equal to T, 0 if x is not equal to T. Take this collection of functions, we saw that this was linearly independent. Is this max? We saw K is linearly independent. Is this maximal linearly independent? Or not? What do you think? This is exercise. Is this maximal in? Huh? Every element is a maximal element. How do you say that? But I am asking whether this is a maximal linearly independent set. That means, is there a bigger linearly independent set of which this is a part? Is there a bigger linearly independent set of which this is a part? I am going to leave it as an exercise. Okay? Have your weekend ruined by this you may not want to think about it, but it will bother you. Okay, so if you are serious about the course, that's one way of ruining. Most of the teachers ruin your weekends by giving assignments. Okay, sadistic pleasure that teachers get. Anyway, so think whether that's a maximal linear. So okay, so now what I want to say is that the Zorn's lemma is one tool that we may try to use whenever we are looking for something maximal. Whenever we are looking for maximal elements, it's very likely that the Zorn's lemma will come into play. This is one of the strong tools that is used for proving maximal element existence. Okay, that's the next. First, we had the notions of counting, countability, and uncountability, and so on, the cardinality notions. Then we had these notions of partially orders. All these ideas will be used, and I am now going to start. I thought I would finish it today. I'm going to start another set of preliminaries, which was some standard inequalities, which are very crucial in all that we are going to do. So the next, this will be, I will finish it very quickly, maximum next class, but all these inequalities are very special and very useful and very crucial. Okay. Now most of the inequalities that we use in our course, at least, there is a very famous quote by, I don't remember, Polya or Zigo. There is a book by, there was a book by Polya and Zigo. I think it was Inequalities. It is several hundred pages, and that was not enough. Subsequently, I think Hardy and Littlewood wrote another book on inequalities, which also went into 100 pages. And I think somebody made a comment that an analyst spends half the time looking for the inequality that he wants and spends the other half time trying to prove it, because he didn't find it anywhere. Okay. So most of the time they are always trying to estimate and get some inequality. But we are going to look at some very simple inequalities. So what we will start with a very generic inequality and build on that to get all the standard inequalities that we want. So the most generic inequality is that if you take a real number and square it, it will be always non-negative. So this is the generic inequality for all real numbers. And that everybody knows. X squared is always greater than or equal to 0 for all x. And when does that become equal to 0? If and only if x is, let me call that as the most generic inequality 1. In about 10 minutes, I will prove one inequality which is the next level. See, most of the inequalities are built on this by choosing the right x, that's all. You choose the right x's and go on building, you get several inequalities. So now what I am going to do is, let us take two real numbers, without loss of genetic, take them to be greater than 0. We will see what happens when it is equal to 0, if any one of them is 0. Then I will, for notational purposes, I will call the pair A1, A2 as A. Okay? Pair of vectors, a pair of elements. They are real numbers greater than 0. Then what is the average? The average is A1 plus by 2, and that is called the arithmetic mean. Of A1 and A2. So therefore there is going to be a geometric mean. So what is the geometric mean? it is the square root of a1, I will write it as square root of a1 into square root of a2, which is square root of a1 e2. So, what, how do I get the geometric mean? You first code these numbers as their logarithms, okay, and then take the arithmetic mean and then take the antilog, decode. Code as logarithms, then take the arithmetic mean and then do the decoding, you get some number. That is what is called as the geometric mean. So, for example, a1 will be coded as log a1, a2 will be coded as log a2, and the arithmetic mean will be this, which is logarithm of square root of a1 into square root of e2, then take the decoding antilog, you will get square root of a1 a2. Okay. So, that is how the geometric mean is obtained. Code, arithmetic mean, then decode. Instead of straight away taking arithmetic mean, you are doing some hashing, okay, for this, to hide the fact. Okay. Now, you see, I choose x to be square root of a1. Whenever I say square root, I always mean the non-negative square root, okay, always the non-negative square root. So, look at square root of a1 minus square root of a2, take that to be x. What do I get? 0 is less than as x squared, that is 0 is less than or equal to a1 plus a2 minus 2 square root of a1 into square root of a2, or rewrite this, I get square root of a1 square root of a2 is less than or equal to a1 plus a2 by 2, or g of a is less than or equal to, this is a very famous arithmetic mean geometric inequality. This is what is known as the AMGM inequality. Arithmetic mean, geometric mean equality. Now, I will just 3 minutes, we still have 6-7 minutes. So, I will generalize this now. Generalize. How do I generalize this? If you look at the arithmetic mean, I have given the same weightage for a1 and the same weightage for a2, half half. It's like a1 is your sessional score and a2 is the final exam score, or maybe a1 is the assignment score and a2 is the test score. But I would like to give more weightage to test assignment, so I would like to give the weightage instead of equal weightage. So, what I will do now is choose weights. So, let lambda be lambda 1, lambda 2, where 0 less than lambda 1 less than 1, 0 less than lambda 2 less than 1, and lambda 1 plus lambda 2 is 1. Total weight is 1. Now, I am going to define the weighted arithmetic mean as give lambda 1 weightage to a1 plus lambda 2 weightage, and I should put divided by lambda 1 plus lambda 2, which is 1. Okay. So, I get lambda 1 a1 plus lambda 2 a2. Okay. What about the geometric mean? What will happen here? Take the logarithm, instead of half I will put lambda 1. So, this will become a1 to the power of lambda 1, a2 to the power of lambda 2, and then the anti-log will. So, this will be a1 to the power of lambda 1, a2 to the power of lambda 2. That is called the weighted geometric mean, and that is called the weighted arithmetic mean, the weights being lambda 1, lambda 2. The question is, does this inequality hold for the weighted means? Is it true? Is g lambda a less than or equal to a lambda? even after weightage, does the geometric mean get dominated by the arithmetic mean? Okay. This is the question which we will start investigating next time. Then we will show it is indeed true. Okay. That is still true even for the weighted fellows, and then we will use both these and get many of the inequalities that we will be using. But one thing that I want you to observe here is equality holds if and only if x is equal to 0. So equality holds if and only if root equal to root a2, if and only if a1 equal to a2. So equality if and only if both the numbers are same, and the same thing will be true there also. Even in the weighted means the inequality becomes an equality if and only both the numbers are the same. We will see how it goes. Okay. So that is called the weighted. In fact, I would ask you to look at even the following. Suppose I have n numbers. Okay, and I have n weights. When all weights are equal, we get the standard geometric and standard arithmetic means. Okay. So then how would I define the weighted this thing? Lambda 1 a1 plus lambda n an, and the weighted geometric mean as lambda a1 to the power of lambda 1, a2 to the power of lambda 2, an to the power of lambda n. The question is still, is it true? For n numbers, classical or weighted, arithmetic geometric mean, are they comparable in the same way as we did for two numbers? Again, is equality true if and only if now all the numbers are equal? These are questions, but we will first this and use all of them to get very standard inequalities, and subsequently we will look at it and see what it really means finally, and we will have we'll see that we can define variety of means, averages. So the average that we have in mind is only one type of average, simply adding and dividing by the total. There are several types of means that we can define. For example, we have here now, okay, that can be further generalized, and we can have a whole family of means, that averages that one can develop. So when somebody says on an average he is okay, you must ask which average. Okay, so I think I will stop here and I will pick up from there.